by Professor Bertola, University of Padua.
It's really a great pleasure for me to chair this session describing the scientific achievements of one of my first students. So we start with Nanni Bignami.
Sì, right
Here.
Ciao Francesco. Come microfono come andiamo? Questo?
Si mette qua?
No, io sto in piedi.
Sì, no, qua perché c'è la telecamera.
E che cazzo? Devo stare qua? E poi ci vuole un microfono. No, preferisco la canna da pesca. Pointer particularly advanced technologically. Yes, I'll try and be quick and painless, but tell you something about the future of astronomy in Italy. Why not? Why settle for less? Inevitably, here you're very much focused on one particular topic, which is beautiful. Been listening, learning quite a lot, but I have to bring you on a wider scale, inevitably, and I'll try and be extremely quick because most of the work has already been done by the joint work of our scientific council, who produced a document called DVS in Italian, Documento di Visione Strategica, where they put their strategic vision. It sounds like a strategic air command, but anyway, so the document is nearing completion and in a few days will become public, and it will contain an analysis of all of astronomy and then the ideas and priorities for Italy. So, as I say, I'll try and be very schematic, and I'll go by pillars, if you want. Namely, currently there are 5 main pillars of, I'm going to be wrong about the numbers anyway, so don't worry. There are some ongoing pillars now existing, the first of which is, of course, Pride and Joy Galileo, the national telescope, of which has become particularly rich in results since HABS Nord's been installed, and I don't have time to talk about each point, but I'm sure you all know about this much better than I do. And the other Pride and Joy, the Sardinia Radio Telescope, now already approaching the end of the commissioning. It works very, very well. There are some problems with pieces of metal falling down from the telescope, but this is a trivial detail which is now being cured, let us say, because the problem is for the sheep that are grazing under the telescope and receive it. That's all right. And then we have the other Pride and Joy, the large binocular telescope in Arizona, which we own 25%, as you know, which recently has done some beautiful results. For example, has saved the Earth from an asteroid. I don't know if you knew that. There was this asteroid coming somewhere from the depth of the skies, and it was undetected, or at least it was unclear. It was difficult to predict its trajectory, and it was going to go by the sun, very close to the sun, so it was going to be lost, and mankind would have remained with a fear that this object might hit the Earth in 2091. So you say, who cares? But never mind. But because they have a combination, this is the point, a combination of large field of view and high angular resolution, they managed to nail down the object, and they told us that it will not hit the Earth in 2091. Excellent news. More interesting, in a way, are the splendid observations they have been doing on Io, innermost of the Galilean satellites of Jupiter, as you know, which has volcanoes that erupt. It's just that they've done beautiful pictures of that. They're still embargoed, but I mentioned because those would make great public outreach. And then, of course, in this context, I don't need to mention the VLT and its various instruments now coming up. And also in this context, I don't need to dwell too much on ALMA. ALMA has also been giving us some practical problems, more or less, again, with that. No, this is not pieces of metal falling down, but things warming up too much, or some problem of stabilization, etc. Because one never thinks that once you've built a telescope, well, no one except Jorge maybe knows that when you build the telescope, you have to maintain it and make sure that it continues to work. Anyway, so these are, at a broad stroke, the grandest projects which we are working on now. ENAF is working on now on the ground. Let me make a brief excursus on space. And here, of course, inevitably, I have to start from high energy astronomy, high energy gamma ray astronomy in this sense. And let me use this fishing rod to point out the lovely sequence over 40 years of Italy's contribution to high energy astrophysics, including the first ESA satellite, 2 Italian national missions, 2 Italian PI instruments, and with 5 missions currently active, lots of Rossi prizes, etc. I would say this is a line of work in which Italian astrophysics has been doing very, very well indeed, at least as good as all the other lines of work, of course. So let's go right away into the future. Again, in the interest of time, because at the end I have a little surprise for you. And this is, we start now with the pillars of the future. Since we're talking about space, let me tell you the first pillar, or the biggest of the pillars of the future in again, high energy astrophysics, in X-ray astronomy in particular, it's called Athena, or Athena Plus. I can't remember whether the plus sign remains or not, irrelevant. It's a bigger and better XMM. In fact, it looks very much like XMM, I must say. Anyway, that has been recently approved, and now people are fighting for positioning on board the instrument. For those of the young generation who want to do X-ray astronomy of the future, this is the place to be. This is really the place to be. This will see as deep in the universe as the ELT will see. Like years ago, there were other combinations of Einstein Observatory and the NTT, and then XMM and the VLT. Now this will the equivalent of the ELT, very simplifying things, but we have in mind to going in parallel as deep as possible in the sky. But then we have other missions in space astronomy that are now ongoing. For example, I'll go quickly. Gaia, you know all about it. I don't need to mention it too much. It's up there working very, very well. A huge challenge to data analysis, of course, but the people who invented it apparently have some idea how to do it. I don't, but it's irrelevant. They seem to know. And then there's some new dimensions coming in, because ESA has introduced some variability in its mission sizes. So very recently we had this relatively small thing, but very important, Cheops, which Italy participates very significantly. This is a mission dedicated to the characterization, which I think CH means characterization, of the extrasolar planets. The O stands for?
Exoplanet.
Huh?
All exoplanet.
Wow. All right. Never mind. Anyway, the concept is characterizing extrasolar planet. Huh? Good. And then, of course, on a bigger scale, if you want, Plato, which is relatively recently, let us say, being selected, and we're proud to have here in the audience some of the pillars of the Plato mission, and they are already desperately trying to worry about getting resources, not very original, but unfortunately very, very necessary. In this context, well, I'll make comment later on. The space astronomy is not only astronomy of deep sky, let me say, but also solar system, and we have something about the present of the solar system. Venus Express is now sort of plunging, I don't know what's the state, it's been plunging into the thick atmosphere of Venus. Does anyone know what's happening? But anyway, it's been there for, what, 10 years now, right? No, not 10, 8 years, I think. And the mission is coming to an end, gloriously, and so it will plunge into the thick clouds of Jupiter, see what happens. Mars Express also been there for over 10 years now. Cassini, glorious. Dawn, NASA mission of which we participate, and of course the mythical Rosetta. I won't talk about Rosetta because we had been saturated about Rosetta recently. And for the future, we have Bepi Colombo, which is sort of plodding on, slower than we would have thought, we would have wanted, but never mind, it will get there. And then the glory for our solar astronomer, solar orbiter, in which we have invested, we as Italy, the Italian Space Agency of course, but also INAF have invested a huge amount of money and will now start relatively soon, JUICE, the NASA mission on which we have a significant payload participation. So I'm quite happy about the balance of various aims of these missions. But then we have other space missions, of course, our modest but non-zero participation in the James Webb Space Telescope. I say modest with due attention to the people maybe in the audience who work on it. I regret that the Italian participation has not been as big as I would have liked at the time when the choices were made. I think some mistakes were made as a result. Hardware participation, for example, etc., is not as good as it could have been or as Italy deserved. But then that's the way it is. We will participate at the level of data analysis, of course. And of course we have Euclid, which is an extremely important deep sky cosmology mission, which is ongoing rapidly and where Italy has a very significant contribution. Let me say in general that for all of space astronomy, planetology, deep sky, etc., it is fundamental that the Italian Space Agency has, let's say, enough funds to support this part of fundamental research, which it should, by definition, by law, support. We, as you know, have an ongoing problem of a lot of competitive interests on space missions, including defense missions, including applications missions. I mentioned defense mission, I get censored immediately, yes? It's a non-negligible problem for Italy, guys, at least for the Italians, but not only the Italians, the same for Europe. It's a non-negligible problem, the amount of money that is devoted to defense work, which, I underline, is not funded by defense budget, okay? This is the key point. I say it every time. We do not want to use research money to fund defense budgets. We're very happy that the defense funds its own space program within the space agency, fine, but not at the expense of the research money. Just to be very political, as I usually am, of course. Yes, well, okay. Quickly to the next step, something that is very dear to the heart of some people in the audience, SKA, zillions of antennas all over the southern hemisphere. You've heard about it. The situation of the governmental support is not as clear-cut as we would like, but we are trying very hard. Maybe later on I could explain some ideas that we have. One thing must be very clear. There is no way that Italy can do SKA on just standard enough money. We know this very well. Yes, every time we say yes, but I do not see extra money appearing, okay? So, no, I mean, this is a fact. We cannot do SKA other than playing around, being the clever radio astronomers, but we cannot produce antennas and things if we do not have a significant extra allocation of money. And here is one representation. And then we have, of course, the pride and joy of the future, the European Extremely Large Telescope. Okay, here the situation is difficult, as you know, because of our Brazilian friends, etc. I won't get into detail, but next week there will be a critical meeting of the Council of ISO, where the decision about this will be taken. And I have received instructions from the Ministry of Foreign Affairs, from the Ministry of Economic Affairs, from the Ministry of Research and University. Instructions are not money. This must be very, very clear. In the end, if we could take part in the ELT, was because we decided to put some enough money, hardcore money, a pound of flesh. We took out a pound of flesh from our budget to join into this. Otherwise, neither the Ministry of Foreign Affairs nor the Ministry for Finances nor any other ministry would have given us enough money to do this. So the hard choices have been made. I think we're in. And finally, the other great pillars, so the four pillars of the future are Athena, as I mentioned, SKA, ELT, and now CTA. This, so far, is the smallest of these pillars and also the best positioned because it's the one that's already started. Luckily enough, we had one of those progetti bandiera, these crazy things of Minister Gelmini, whom I'm reevaluating day by day anyway. There was at least an idea, a line which we could use. Okay. You all know about CTA, but what you don't know is that now you are going to get... Aspetta, un attimo, glielo faccio vedere, sono pochi minuti ma vale la pena. This is using Mount Etna as a support for a telescope. You can see Mount Etna. And this is the first of the CTA telescopes being integrated on Sea Mount Etna, smoking at times. Incredibly enough, this was done on time and within budget. And it's the first of the 4-meter class telescope of the CTA, the Cherenkov Telescope Array, which is now undergoing calibration, but it's already taking data, it's already measuring, in a beautiful spot called Serra La Nave, which about 1,800 meters on the slopes of Etna. Great place. I strongly recommend that you go. Incredibly, this is a program which we have done on the basis of money obtained for this program, exactly with that amount, exactly on time. We have produced a splendid machine which has now been bought as is in one copy by the South African and in 2 copies by the Brazilians. We are going to produce 4 more, and all 7 of them will be located as a mini array at the bases of Paranal in a flat sort of part. It needs a flat part, but there's plenty of room between Armazones and Paranal. This last part that I said is not decided yet, so please don't take it as it was true. Okay, so this is the machine, and you see it has rather simple optics. Still, it's a 4-meter thing, and it moves around. It has some focal thingies, has data collection. It's a telescope, okay? Produced in time and on budget. And I think I should thank explicitly the group of industries that did this under contract of INA. Okay, thank you very much.
Okay, thank you, Nani. And the next contribution is about...
I can take questions if they want.
Yes. There are questions?
Good.
At some point last year we discussed some participation of INAF in the Sloan 4 project, and there was a member of the executive committee for that, and so I was planning to talk to you anyway. It doesn't need to be to cover a full national participation, but you could just pick a few distinct members that I would think Naples is one of the first in front because of its experience on survey. Would you think INAF would be open to buying finally one of the Sloan projects? Sorry for the very open
No. I am certainly open to, as you say. I confess my ignorance, not of course of the Sloan project, but of the size. Yeah, when asked about the importance of the Pope in World War II, Stalin said, "How many divisions?" So, how much do you want?
Shall I give you a figure?
Yes, because otherwise we can talk. I mean,
Yeah, well, I talked to Francesca Matteucci extensively
that
about
doesn't
that.
help.
Doesn't help. So let's say a full...
No, I mean, sorry, it doesn't help. Means it helps creating a beautiful scientific case, but
Yes.
unfortunately Professor Capazzoli, myself, and a few other fellows have to...
Yeah.
Yeah.
So a full institutional participation would be $1 million, okay, which you can scale down to a various type of MOU. It doesn't need to be paid cash straight away.
Thank you.
Yeah, no. Well, even Chile is buying like this.
Even Chile. Well,
I
what's
say
your
even Chile
mouth?
because they are building an instrument, which is the
Yes,
MOU.
but
So
the
it's like
expression even Chile.
They are fundamental.
Okay.
This by
Maybe have you
Yeah.
written a letter saying, "Dear Enough, I would like $1 million"?
No, I don't think. I don't think you should consider enough because we don't need that many individuals. But probably we should target specific people who are going to bring real expertise, which can be in
Good.
kind. So
Let's talk about it.
let's talk about it. Okay.
Questions? Okay, so we move to the paper of Giuseppe Longo, which is describing the contribution of Massimo to astronomy.
Well, I don't know whether you can hear me, but I must tell you the truth. After more than 30 years in the business, it's one of the few talks which I feel uncomfortable giving. I mean, it's, also because the chairman is a mentor of my mentor. So in this moment I am embarrassed to the square, which is not real. I mean, I start this session about the contribution of Massimo to astronomy, and since, let's say, we've been friends for more than the duration of the average marriage, I think that I'll be the first one who we find some difficulties in restraining from some commotion. I mean, Massimo started the business 46 years ago. And he had truly a running start. As you can see here, this is the ceremony for the graduation in Padua, where he is chased because someone is trying to kick him. And that was really, I think, the beginning of a long run. The one on the right, you can see it's unrecognizable, but time is not very clement on people, sometimes. But Massimo graduated in Padua, which at that time was the center of astronomical action. I'm sure I'm not mistaken. It was the center of astronomical action in Italy, and most of the relevant astronomy was made in Padua, where Professor Bertola was among the first to start extragalactic astronomy, and therefore it's not a surprise that Massimo did his thesis with Professor Bertola. And being there, he was had the opportunity to meet many leading scientists worldwide. This is also why, since the beginning, Massimo had a very international approach to research. I am not going to enter into the details of his work, also because after me there will be Gianpaolo Riotto speaking about his Padua years, I would say, and then there will be Massimo della Valle and other people, his former students, who will. I must say this, when we decided to organize this session, I began to receive email together with Napolitano saying, well, I must speak because I have with Massimo the paper which has the highest number of citations. Then I have with Massimo the paper which is most important. And so again, we could not let everyone speak because everyone wanted to share the moment because somehow Massimo was crucial for his life. Massimo started at a very difficult time. Students cannot imagine how difficult it was to do astronomy. I mean, few people in this room can remember it. There were no computers, not to mention graphical display or color displays. Most computation was done by hand, and also observation was done in a different way. I still remember, I found it exhilarating when Massimo told me that one night observing at the Santiago telescope, he lost his eyelids because he got frozen to the eyepiece, because he was driving the telescope by hand. Massimo participated in very active life, cultural life of the Observatory of Padua, and very soon became a protagonist. Among his earlier works, I just want to mention a few and say a few things. I think that other people can do this much better than me. His first paper was this one, together with Professor Bertola. And 2 years later, there was a seminal paper. I'm always surprised by the fact that when he speaks, he forgets about this paper. This paper really started the revolution. I still remember the proceedings of a meeting, a Yale meeting on galaxy structure, where, if I'm not wrong, Beatrice Dinsley spoke about a Copernican revolution in the field of galaxy dynamics started by this paper. This paper was, I went very quickly through the literature. I mean, since not most astronomers are very honest, I would say, out of this paper have come more than 10,000 papers. And unfortunately, they not always quote this paper as a starting point. So I think that if Massimo must be proud of something, this is one of the things which he really was crucial for everything which followed. Here you can see the high technology which was used at that time. Massimo sitting in front of advanced acquisition system, as you can see, done by eyes, taking numbers. Corky is laughing because he remembers exactly what we are talking about here. Then another seminal paper was this one, always by the couple, Bertola Capraccioli, which was again another crucial point in the stellar dynamics. But as I say, I am not going to spend very much about his scientific contribution because I think that there are other aspects of Massimo which are at least as important as his scientific contribution. Other people will do that. On the right side, black and white, we have the first picture of Naples, of Napoli, Massimo in Naples. At that time, I just graduated and I wanted to start a career in extragalactic astronomy, and therefore I asked Massimo to come and give a lecture in Naples. This was his first morning in Naples. And it was the beginning of a long-lasting interaction of Massimo with the Neapolitan astronomical community. And he first began to grow the interaction. I mean, it's difficult to imagine this observatory the way it was in 1981. There were 13 astronomers, and was basically a beautiful box, but completely empty. The line of research were very obsolete. I mean, there was only a group of solar physics, but then, you know, stellar evolution was doing rather standard things, but there was not much more. And therefore, we began to grow, also thanks to the contribution of Massimo, who was crucial in starting the extragalactic astronomy in Naples. And immediately after, I got involved in what we call the Texas years. Massimo in Palo had become acquainted with Professor de Vogler, was his lifelong friend. So he spent many years in Texas, and there he did another important piece of work, which I think it's worth to remember, which is the best photometry ever made. I think that even nowadays it's difficult to do better, but I would like to stress that it was done with photographic plates and with Schmidt plates, no CCDs. And it is a photometer which extends 14 orders, 14 surface brightness units from 14 to 30. Something absolutely outstanding, which was also the first demonstration that for a non-elliptical galaxies there is a perfect R2d1/4 law, which was a sort of surprising, outstanding result. I mean, I think that that time, I mean, it's impossible to speak about someone we have known for 30 years without making personal recollection. And I still remember when he was a city in Texas, and since it was very practical, you know, and I tried, you know, to make him feel better, and I would try, he was at the fever, 41 fever, I was trying to feed him with hamburgers and French fries. That was really something which I never forget in my life. Then Massimo became closer and closer to Naples. In 1989, we hosted in Naples the first international meeting in this field in Naples, and also one of the first in the south of Rome, about morphological and physical classification of galaxies. And here you see three circles marking Caraccioli, Bertola, and Piotto, who will speak after me. I mean, so it's many things have happened since then. And also, so always since that time, I began to discover I was not a student of Massimo, and I regret this. I was always a collaborator and a friend. And but I discovered he was a good teacher when he was trying to explain diskiness and boxiness of galaxies using a lemon in front of a sort of astonished audience. And that was really a highlight of the meeting, I would say. And with Massimo, even before he became director, scientific life in Naples began to boost, at least in the astronomical field. Together we started a permanent seminar in cosmology at the Institute for Philosophical Studies. Then people began, at least in our group, began to travel extensively. Here you have a few pictures from the first meetings which we were attending abroad. So Massimo really broadened our horizon. And there is one thing I want to mention, that if you go to the huge publication list of Massimo, you discover something which is impressive. I think you have only one paper that is a single author. Massimo has always had oral value. He always liked to share knowledge, to collaborate with people. He wanted to have people close to him because it is in his nature, basically. It was not, there was not even a specific benefit coming out of it. He just likes to interact with people and to collaborate with people. Okay, here you see. Here we are already approaching I think the first two pictures refer when he was already director. As soon as he became director, Naples began to have a completely different scientific life. We had international guests. You can see here David Malin, Ivan King, Dennis Sciama, Ralph Bender, Jean-Luc Nieto, which were all people which do not, well, I think even ignored that the astronomical observatory of Naples exists. Therefore, I don't think I can summarize what Massimo has done for this community and for this town, in some sense. He found an observatory which was basically deserted, and when he left, there were more or less 20 units more of staff personnel, not to mention the movement of PhD students or students. He created from scratch a group of university. There was the first member, but then other people like Maurizio Godino, Giovanni Esther, people joined us, because he was capable to get something which I think has happened only once in the history of the Italian university. He got a special grant from the minister to fund the university, just to open astronomy position. It was a 700 million lira at that time. And it was done not out of a political power. Political connections did not exist before. It was just sitting hour and hour in the hall of the ministry waiting to be received and to make a strong case, and he succeeded. Then the observatory began to participate into the international projects. The wide field imager was the first one, then we participated in the National Telescope Galileo, then we had the VIRMOS, which then became VIMOS, then the fantastic, but I'm not going to speak about VST, it was made, well, this meeting is about VST, so there's not much to say, then the planetary nebula spectrograph, and many smaller ones. It was incredibly hard work. I still remember how much Massimo was working. We were exchanging phone calls often at 3 o'clock in the night, something like that. Not always. Now and again, Massimo was also, bringing his joy of life to whatever we were doing. I mean, it has been really beautiful. Obviously, no one is perfect. There is one thing which Massimo is really not capable to do. He's not an athlete. Here you can see him when he's trying to lift the cannon in Berlin, together with Bruno and Parola. Well, it was fantastic. Three of them tried to lift this thing, and the youngest guy, the most athletic one, also trying to take pictures. It was a sort of contradiction in terms. But I think that this life can be summarized like that. He's brave and determined. I still remember when I think that to come from power, which was at the center of Italian astronomy, to be the director here was an act of bravery. Massimo wanted to build something. I still remember one night in the guest house of the observatory, Massimo sitting in front of me and saying, "Peppe, this must be the most stupid thing I've ever done in my life." Then the facts have proven him wrong, because he did it. He has always been very passionate, whatever he has done, and enormous curiosity. After a few weeks in Naples, he knew Naples better than I. I mean, Naples, Massimo is curious about everything. Energetic and hardworking. He likes to work with people. But what I think Massimo has been absolutely outstanding is as a professor. Okay, these are peoples which, if they are astronomers, they owe it to Massimo. And I think this is something which needs to be taken into account, because all of us who are professors know that our students are at the center of everything. Why did I put myself? Not to show me anything. This was my group in 2009, a mixture. Because at some point the scientific interest of Massimo and mine diverged. We stayed into astrophysics. I went more to computer science, what is nowadays called astroinformatics. But that is my group in 2009. And I made a simple computation. Massimo has had more than 70 students. If we take also the siblings, so this applies also to Professor Bertola and to the second order. Since we basically try to mimic what our mentors teach us, I mean, the imprinting of Massimo is left also in our students. So, can I ask a favor of you? all the students of Massimo and all the people who have all their position, could you please stand up? Ragazzi, piedi. Ok. Forza. Massimo. Ok. Massimo, look around. I think that this is the best thing which you could do. So let me finish with this sentence, which since Massimo, due to Rosanna, has developed an artistic interest in his curiosity. This is a fantastic sentence in a letter by Vincent van Gogh to his brother, which I think it's very specific to the life and work of Massimo. I mean, faith, energy, warmth, knowledge and culture are the reasons why it is worth to live. Therefore, I would like, on behalf, thank you.
Thank you, Giuseppe, for this very warm and lively account. I don't think there is need to ask a question. So let's move to the next talk by Giotto.
Okay. So it's difficult to say something more after the talk. And I decided to have a different approach, no slides, also because I don't have all those nice pictures. Second, because nothing of what we say will remain, which is better. And third, because, okay, I knew about this just a few days ago. I was not going to accept, but at the end I decided it was absolutely not appropriate because I really owe a lot to Massimo. So I want to say a few things. And last day I was thinking to my first memory of Massimo, and I have a very clear picture. A room, a little bit hot, because Massimo liked to be in a warm place, with a lot of smoke. I mean, the smoke was above your head, but because I was sitting in front of him in the desk, because if you are standing, because Massimo at the time was smoking a lot, which was a nightmare for me because I suffer from asthma, so you can understand how difficult it was to stay inside this small office where he was giving also his lecture and so on. I'm not telling you this because I want to tell you about Massimo business, but because I perfectly remember one day towards the end of December I don't remember the year, but you surely remember the year. We were at lunch and Massimo told me, starting January 1st, I will not smoke anymore. And believe me, he was smoking 80 cigarettes a day, perhaps more in some periods. And I told him, I don't believe you, we are joking. Well, believe me, since January of the following year, I've never seen Massimo to touch a cigarette, which is astonishing. And this tells you that Massimo is a strong person with a strong will, very determined in what he wants to do. And I think this is a good part of his success and something that I've appreciated, and you need to learn this very soon if you want to collaborate with him, because it can be tough if you don't accept this kind. But it has been very important, also for all his students. So as Pepe said, Massimo had his laureato degree in Padova in '69 with a thesis on the Apple constant. At that time there was no PhD in Italy. He had immediately a position as associate or something like that it was called. And he started his research under the supervision, the strict control of Professor Bertola, I'm sure about that. And Professor Bertola started, he learned how to do research, and he put the basis of, his strong and still well-present impact in the international scientific community. And there is one thing that I want you to note. In part, you see it already reading the titles of the talks of a few students, or former students, sorry, that have been working with Massimo. And you see that, okay, he started to work on galaxies, as Weber reminded us, on morphology of galaxies, on dynamics of a galaxy, on the spectral distribution of light from galaxies. I want to remind you another important paper by Massimo Capaccioli and Francesco Bertola, which is the paper on, coming from IUE data, where they put the basis of the important problem, which is the UV upturn in elliptica and SS0 galaxies, a problem which is still open. We don't have a clear solution for this problem. Maybe we can help with the recent results on globular clusters and helium-rich hot stellar population. So we started to work on galaxies, but then, if you look at the many other different subjects that he touched in his career, particularly when he was in Padua, it is astonishing. Of course, he worked on globular clusters. Okay, I didn't want to talk much about globular clusters today because we had the talk yesterday, but thanks to the supervision of Massimo, we had, I think we published a few important papers, in particular on the mass function of stars in globular clusters, which put the basis of our understanding the evolution of the stellar population inside globular cluster and the interaction of globular clusters with the galaxies, and how this interaction is changing the stellar populations of globular clusters, photometry of stars, photometer diagrams, dynamics of globular clusters. But then there is a series of papers, I'm sure Massimo will tell more about this, on novae. There is a series of papers on C-fields. And not to forget the series of papers on the astrometry of Pluto, which started since the beginning of the 70s and lasted till middle of 80s. So many different interests, many scientific works, which still, some of them are still cited and remain for their importance. So not only a person with a strong will, but also with a large interest in astronomy, and not only in astronomy if you know him. Okay, it's a different story. Working on these different subjects, he has been able also to write a large number of students, as Becker reminded us. Students that sometimes had tough time working with him because strong person. We were all in a big office, which was another important part, I think, of the work that's been done, particularly in the 80s. We were all together, and I think all of you, all the former students who are here, students and even staff astronomers remember the days and the nights, because we were working till very late, close to early night, every day, sitting close to Massimo, writing a paper. That means, writing a paper means, for Massimo, start to work to every single, on every single sentence, on every single word, change that word many, many times, change the sentence many times, reverse the sentence, change the order of the sentences, and after that was the easy part. The name was coming when we started to reread the paper to see if everything was clear. And at the point, we arrived at the point where he said, "What did you write here? This sentence is not understandable at all. You can't write something like that." Massimo, you wrote it a couple of days ago. No, it's impossible. We have to redo it, everything. It has been hard, but I think that all of us learned a lot in this way. It has really been an arena for us, and we learned a lot, not only how to write a paper, but we learned a lot also how to organize a scientific work, how to properly present it. And I think that these are the most important lessons that we have from us. Organize the work and be meticulous in what you do. Don't leave anything aside. Work on everything. Be sure that what you are writing is exactly what you have, and try to extract the best from the material that you have. As I said, it has been hard, but it has been very important for us, at least for me, but I'm sure for the others. As I said, many students have been working and at the level of starting with undergraduate students. Some of them then became PhD students and so on. And towards the end of the 80s, the number of students that were working with Massimo was so large that we could organize our soccer team, real soccer team, 11 people. We were playing, it was the Capaccioli team, we were playing every week against the rest of the astronomers in Padua.
Losing systematically.
No, that's not true. That's not true. That's not true, because they were very good players, not me of course, but they were very good players. And Massimo was very fond of that, because he found a sponsor, I remember, and the sponsor could paid for all the entire, sweets and t-shirts and socks and trousers and so on. And it was very fun. Okay, another thing that I wanted to mention is, Massimo started to do research immediately after the laurea, but started also to teach immediately after the laurea. I've seen that you have been teaching rational mechanics, cosmology, physics, even in the mathematics, in Padua, in Lecce, and in Venice too, the architecture faculty. But since 1976, Massimo had started to teach celestial mechanics. Okay, I want to say this for two reasons. First, because you can imagine that it's not easy to teach celestial mechanics at the University of Padua, that is the university, that is the University of Beppe Colombo. But I must say that the celestial mechanics lectures by Massimo were wonderful. They were very well organized. They were very, it was fun to follow those lectures. The celestial mechanics is quite difficult to teach. It's even more difficult to understand. But all of us were really happy to go to these lectures. Massimo has the capability to teach even very difficult concepts in a very nice way, in a very comprehensible way. And this at all levels, at the levels of students at the university, and at the levels also of public lectures, as many of you probably have seen yesterday night. So this is another quality that Massimo has, and I think very few professors have this capability of teaching. And I had to substitute Massimo many times later on in celestial mechanics lectures, and then I had to teach celestial mechanics for 2 years. And I never understood how, I was using his lectures, but I never reached his level in teaching. To say everything, I don't want to say. Okay. I want to say, but I don't remember now. Anyway, as I say, we as former students are very happy to have been, raised by a person like Massimo. We are trying now to convey all the lessons also to our students. And you have not only your students, but you have also the students that your students have created. And the number is really increasing. So I need to thank you, and many of you former students for sure are with me, and Wimberg, thank you for what you have done for us, and as a teacher, as a supervisor, and in a sense also as a friend. Thank you.
Thank you, Paolo. We move now to Massimo della Valle.
Thank you, everyone. Well, so the title of my talk is Not at the Massimo with Massimo. Of course, I'm Massimo too, but I'm not going to talk about myself. The story begins in 1986 when the other comet was back, and I was going to Soviet Union to start my PhD. This is a 2.6 meter telescope in Bureau Observatory. This is the 6 meter in Zelenchuskaya, and in one year time I had also time to improve my chess, and all these activities were under the supervision of these are the original leaders of the meeting of Professor Leonida Rosino, Massimo Capaccioli, and the chair of the PhD program at that time was Professor Francesco Bertolo. During my PhD time, I wrote 4 papers with Massimo Capaccioli, mostly dedicated to novae and supernovae. And I'm going to spend a little bit the papers devoted to novae M31 and the Large Magellanic Cloud. There are other co-authors that are here in the audience, Mauro Donofrio and Enrico Capellaro. I think Enrico will comment Friday about the paper on Virgo and Coma cluster. I have organized my talk this way. I will present the old result and then compare them with the new ones. Then I will comment about the later studies that can be considered remarkable byproduct of those papers in which Capaccioli was not involved. And then, and finally, I have 2-3 slides on extragalactic nova with the ST. First of all, I want to remind you, for people who are not familiar with nova business, what is a nova, a classical nova. A classical nova is a cataclysmic system formed by a white dwarf, which is accreting material from a low mass sequence star. And when the pressure at the bottom of the accreted layer is of the order of 10 to the 19 dyne per centimeter square, immediately the violent thermonuclear runaways start, and the major fraction of accreted material is ejected with velocity of the order of 1,000 up to 5,000 kilometers per second. All novae are recurrent novae, with the time scale of the order of decades up to 1,000 years or 100,000 years. in such a way that, let's say, the more massive is the underlying white dwarf, the shorter is the recurrence time. This is the first paper, probably the most important. Oh, by the way, where is Beppe Longo? He's not here. He's outside. Okay, I agree with Beppe Longo's statement that Massimo like to share the knowledge, so I had to add that, especially as first author. This is good. Just kidding, just kidding. But I mean, he served a perfect assist to me. I couldn't miss it. Okay. These three items were taken on in that paper. The study of spatial distribution of nova inside the paradise, the distance to M31, and the measurement of the nova rate in M31. This is quite important parameter because it is connected with some of the properties of nova systems, like the number of progenitors, the recurrence time, the mass of white dwarf, and all of these are relevant for the possible connection, if any, with Taiwanese supernova progenitor. This is the current status of extragalactic nova survey. I show this because I want to compare with the situation when we started to work together. There was almost nothing. And this is the reason for which this paper is considered still today one of the pioneering papers for the study of extragalactic novae. Is still receiving a considerable number of quotations, but what I like more is that even this year, this paper has been downloaded once per week. So that means that this paper is still alive. Okay, let's move to the first item. So M31 nova population assignment. Before our paper in 1989, there was an indication about novae in M31 that belong to an intermediate or disk population or to a halo population. On the basis of this new survey that has been obtained with, of course, together with Professor Rosino, he started in the 70s and 80s, on the basis of 40 novae, we were able to produce this plot. Basically, you see here the surface brightness profile of the disk in the blue, and red is the bulge, and this is the surface, the nova surface density that overlap of the bulge profile rather than the disk. So the conclusion was that at least 85% of novae in the M31 belong to the bulge. This result was confirmed some years later by Schachten and Irving. Of course, not in all galaxies, nova population is mainly producing the bulge. For example, in this paper wrote by Mike Shara, Alan Sandage, and David Zurek, they found that, for example, for M81, most novae are probably producing the disk. And also there is some extreme cases like M33, that is a bulgeless galaxy for which, by definition, novae have to be produced in the disk. More recently, we started a survey on Andromeda with XMM and Chandra, and we found that, for example, classical novae are the major class of supersoft X-ray sources, and this is not trivial because supersoft X-ray sources are considered potential Taiwanese progenitors. And so we were trying to investigate if there was a different behavior at X-ray wavelength between disk and bulge nova, and unfortunately we didn't find something significant. There is a hint that the distribution of the effective black body temperature of disk nova is different from that of bulge nova, but is only 90% confidence level. Let's move to the Nove has these indicators. The idea to use Nove as this indicator came from McLaughlin in a paper of 1945. He found that the magnitude and maximum of Nove correlated with the rates of decline, in the sense that the most brighter is a nova at maximum in terms of absolute magnitude, the faster is the rate of decline. So what we have done was to build up the maximum magnitude versus rate of decline relationship for Nove in M31 to compare this relationship in apparent magnitude with the absolute calibration of Nove in the Milky Way, and the distance had been obtained by Julie Cohen through the nebular parallaxes. Of course, we have fitted the Julie Cohen Nove with our fit, this S-shape, reverse S-shape relation, and we found a distance module of 24.3 plus minus 0.2. That it is about 7% shorter than the modern estimate, modern measurement. We did the same exercise with Nove in the Large Magellanic Cloud. This is the relationship. We compare with the galactic Nove, and we determine a distance module of 80.70 plus minus 0.2. In this case, our measurement is 80% larger than modern measurement of the distance toward the Large Magellanic Cloud. Byproduct 1. We started to ask ourselves what are the physical parameters that determine the strength of the outburst of a nova. And from a theoretical point of view, there are many. The mass of a white dwarf, the accretion rate, the temperature of a white dwarf, the strength of the magnetic field, the composition of the accreted material, and the mixing process between the accreted material and the underlying white dwarf. When we plot the maximum magnitude versus rate of decline relationship, which is a universal relationship, and this is why we can use Nove as these indicators. Well, in this relationship, there is more, and this is something that we have reported in our paper on Nove in the Large Magellanic Cloud, that the relation is differently populated. But of course, someone can immediately tell, well, that this is a bias, an observational bias. This is wrong, because it will be a very strange observational bias at play, which allow us to discover bright objects in nearby galaxy and to miss the faint one, and on the other hand, to miss bright object in a more distant galaxy and to detect the faint one. So this is not due to an observational bias, but is an effect of the nova population. Here we have these novae, so more massive white dwarf, this plus bulge, and only bulge, so light white dwarf. If at first order approximation, we assume that the more massive is the white dwarf, the more powerful is the outburst, this is the nice fit that we get. And I told you that this is a byproduct, because as you see here, without the previous paper on M31 Nove and LMC Nove, we couldn't get such a nice theoretical, such nice match between observation and theoretical fit. And this is quite important, If you look at page 24 of the Holy Book of people studying Nove, the Galactic Nove by Cecilia Pangaposchi, you see this speed classes of Nove, which basically are just a morphological classification of nova-like curve. But now, the speed class of Nove have a physical meaning, because they are related to both spatial distribution and the mass of the white dwarf. The final point, nova rays in M31 and the supernova 1A connection, if any. On the basis of 172 objects in the paper on nova in M31, we determine a rate of 29 plus minus 4 novae per year. The current measurement, I'm not really convinced about it, but people looking at M31 for microlensing searching have determined the nova rate as byproduct of their own survey. They found about 60 nova per year, so about twice what we got, but no change in spatial distribution. So both nova and M31 are still producing the large. And this is, as I told you at the beginning, rate is a particularly important parameter, because you relate it through the recurrence time to the number of progenitor. And the number of progenitor is the quantity that we need to understand there is a connection with the progenitor of 1A supernova. Byproduct number 2. I found this in the web. One bag of trash is equal 1 liter of gasoline. I think that in a few years here in Campania we will be like Texas. This is my. I was just thinking about how to make money. Anyway, first of all, I have to make a short one slide introduction. One of the most hot topic in modern astrophysics is about the progenitors of supernova 1A. So because there are two competing scenarios, two possible scenarios at play. The double degenerate, in which the Taiwanese supernova is produced after merging of two white dwarfs, carbon-oxygen white dwarfs, or the single degenerate, that means a white dwarf plus a main sequence or low-mass main sequence companion. That means a cataclysmic variable system, so a recurrent nova, symbiotic systems, or supersonic ray sources. In '96, with Mario Livio, we have used again, as a seed, the paper on nova in M31, the paper on nova in LMC, and we conclude that the recurrent novae are not a major class of progenitor of Taiwanese supernovae. And this was confirmed by Bernie Schafter a few months ago, that they, through a completely independent analysis. Recurrent novae are not progenitor. 5 minutes and finished. 2 minutes and finished. Okay. 1 week ago, Shabib family has published this nice paper. The most important thing is that the overall process of mass gain by the white dwarf has an efficiency of just 9%. This is an extremely important result, because if you want to grow up a white dwarf with 1 solar mass to the Chandrasekhar mass, you need, with this efficiency, a donor of about 5 solar masses. And this fact immediately rule out all the novae as a possible progenitor of Taiwanese supernovae. With maybe an exception, only the most massive massive white dwarf, the one that are already very close to the Chandrasekhar limit, for which we need a donor at about 1 solar mass. Observation can help us a lot to support or let's say, or disregard this scenario. Look at this paper by our friend Vedon Lee. He was looking on the pre-discovery, pre-explosion images of HST, the location of explosion supernova 1A 2011 FE in M101, and they concluded that this, because they didn't find anything, they conclude that this observation rule out luminous red giants and the vast majority of helium stars as the mass dominating companion. In other words, they support the double degenerate scenario. So now I'm not telling you, I'm not claiming that Taiwanese supernova come from a double degenerate rather than a single degenerate, but there are supernova for which, for sure, we can exclude the single degenerate scenario. The last two a few slides. The SAT perspective. Well, we know that novae are good because they are very bright. They occur in all Hubble-type galaxies, wide surface, only in spiral, and the cosmic scatter of this magnitude maximum versus rate of the kind relationship is smaller, or 0.17 magnitude. And of course, these are nova observations are time-consuming. This is a plot that I like. I did some time ago. This is the time that we need to make a light curve of a nova. When we use old technology like photography plates, we go from 20 to 40 hours to make a light curve of a nova. Van der Berg and Richard in 1987 using CCD in Virgo, they used about 4 hours per nova. In 2002, 2003, with G. Mosey and VLT, we observing nova in Fornax. We spent about 2 hours per light curve. VST has the capability to achieve a light curve, a complete coverage of a nova evolution, atomic nova evolution, in 4 hours. So using the rates, the current rates, I have simulated this massive momentum versus rate of the kind of relationship, simulated the light curve and 2 blocks of observations, here and here there is the full moon, and we can calibrate 14 Taiwanese supernovae in 10 galaxies. There are multiple events with galaxies with Hubble types from elliptical to Magellan spiral with about 1,280 hours. That means 50 nights per year per 3 years. That is not... Okay, I want to finish with the presentation letter that Professor Capaccioli did to me. I'm not going through all of this, of course. But there is a particular statement. This one.
Quello che ha apprezzato in me, I will translate you in English, but first I have to tell in Italian. Quello che ha apprezzato è stata soprattutto la garbata indipendenza intellettuale. That I will translate. So he liked my way to be, my polite, gentle independence of mind. This is one of the most beautiful things that someone wrote about me. And that's why after so many years I still keep in my files this memorandum, this letter. And I use this as a guideline when I have to choose a collaborator. I want that he has or she has polite independence of mind. Grazie.
Can I remind remind you that the other speakers need to be time, because otherwise we are running late.
Yes.
Thank you very much.
So the next contribution. Seafields and distant islands.
Quello di qua?
Sì, sì.
Miracolo non avviene. C'è un problema di display. Come viene?
Vabbè,
Dimmi.
non muovete questa spezza, questa in modo che viene inquadrato.
Io devo stare qui.
Sì, quando ci sta la luce, perfetto.
Prego.
Okay, I will speak in this talk. I will speak about some recent results concerning the extragalactic distance scale. My interest in this field dates back to many years ago, about 20. During my graduate thesis under the supervision of Massimo, and I worked on the CFID of NCC 5109. I was the first student, Napolitan student of Massimo, and after this work encouraged me to study in more details the possible dependence of the CFID properties from the host galaxy.
While to study classical CFID, we know that they are pulsating stars in the stability strip, and they are population 1 stars. They are very easy to detect because are very brighter, have characteristic light curves with a large amplitude, and overall they obey to a period luminosity relation that can be used as distance indicators. The variables are, in particular, classical CFID for population 1 stars and Lire for population 2 stars, are very important for the cosmic distance ladders because they represent the first rung of this ladder. And we need more secondary indicators to reach cosmological significant distances where it is possible to determine the constant, the Hubble constant. This is a very famous plot produced by the HST key project on the CFID extragalactic distance scale. In green there is the range reached from the CFIDs used to calibrate a number of other secondary indicators to obtain a very solid value for the Hubble constant. Okay, the CFID-PL relation was traditionally considered universal, calibrated on the CFID of the Large Magellan clouds and of our galaxy. But in the 19th, with the advent of the HST, many CFIDs in different galaxies in the Virgo cluster were observed, and these galaxies cover a large range in metallicity, and we had much evidence that CFID properties depend on the metallicity of the host galaxy. We have many open problems on the CFID distance scale. The period luminosity relation dispersion due to intrinsic factor as the field width of the stability strip, but also due to the differential reddening in the observed galaxies and due to pulsating of the light curves, for example. The error on the metallicity and reddening due to metallicity and reddening effect can reach 15%. And the use of Large Magellanic Cloud as reference CFID sample can introduce many systematic errors due to the large reddening and metallicity spread observed in this galaxy. So we can have a solid, to solve this problem, to have a solid theoretical scenario, to observe in the near-infrared bands where the effect of metallicity reddening is small, and to adopt a CFID sample alternative to the LMC1. In these last years, it is used the Galaxy NGC 4258, because for this galaxy we have, which we have observed CFID, HST observed CFID, we have an independent geometrical distance based on a master. With the pulsational group in Naples, we compute an extensive set of nonlinear convective pulsation models covering a large range of metallicity and masses, and these models allow us to obtain all the observables, such as light curves, periods of mean magnitude, to produce period luminosity and period luminosity color relations, to be compared with the observational one, to give an interpretation of the observed pulsation properties, but also to give a theoretical calibration of the extragalactic distance scale. Okay, this is an example of the stability strips that we can produce for different chemical composition, and we see that the stability strip depends from the metallicity and helium that we adopt. We can produce simulated period luminosities for each filter we need for each metallicity. In this example, we have the metallicity representative of the Magellanic Clouds and our galaxies, and we can see that the slope of the PL gets flatter as Z increases in this direction. And the PL dispersion and metallicity dependence decreases moving from optical to near-infrared bands. So it will be useful, using the near-infrared band. These results are in very good agreement with the observational ones. Okay, for example, at very low metallicity, we found that the effect of the metallicity on the period luminosity saturates. And this result, this theoretical result, was confirmed by very recent observations. This is observed. Another application of this pulsation model is to a CFID sample from recent collaborators. this work is very important because RIS and collaborators obtained the Hubble fossa with an error of 3%. They use optical and near-infrared data observed with HST for 8 galaxies hosting type 1a supernova. And they use for the 0 point the galaxy NGC 4258 with the master distance. Okay. So we produce the PL, the period luminosity for these are simulated the period luminosity for all the HST filter, and in particular it is worth to notice that in the H band, the corresponding of the H band, we have that the dispersion of the PL is very, very small, almost negligible. And then for this PL, it's very useful to be applied for infrared distance modulus. A comparison of our models, this purple line and for the PL and the blue and red line for the strip, stability strip, with the NGC 4258 sample from RIS, show a very good agreement between pulsational model and observations. But for the other galaxy, comparing the observed CFIDs with the theoretical stability strip, we found that for the more distant galaxy, we have that the CFID sample appears bluer and brighter respect to the expected. And this is probably due the signature of a crowding effect increasing to larger distance. Also in the optical bands we have the same problem. For the stability strip we have that the CFID sample appears to be bluer and brighter, but fortunately, yes, this effect is negligible in the period luminosity relation that we use to obtain the moduli. So we re-obtain the moduli of this, the distance moduli of this galaxy applying the theoretical relations, and comparing our result with RIS et al, we obtain, as we expected, a discrepancy at larger distance. The H0 value that we obtain is this, with a very small error. This value is in a good agreement with the more recent evaluation of Hubble constant, in particular with the evaluation with the CFIDs and the secondary indicators from RIS et al. And Friedman et al. But it is worth to notice that to obtain this value, we cannot use any secondary indicators, but also pulsation theoretical model applied directly to the CFID sample. Okay, to conclude the last slide, because variable stars are very interesting also as population tracers, and example of this application are represented by the survey STREG at VST and STEP at VST, where I have involvement. And this survey will be presented tomorrow in the morning by Marconi and Ripevi. Thank you.
Thank you very much, Federica. We move now to Mauro Donofrio.
Ready? Okay. First, let me thank the organizer for this beautiful meeting and for the opportunity of speaking about my work as a student of Massimo at the beginning of my career. This one? Okay. When I met Massimo in Padova, he was already a leader researcher in surface photometry of galaxies, and as Pepe Longo reminded us, he published already several important papers with Professor Bertola, Professor Barbon, and other colleagues. And he started to work in Padova with surface photometry of galaxy, and he teaches us this technique. And all what I know about surface photometry is due to what I've learned from Massimo. And these are several papers that have been mentioned before. So I was a little bit surprised when I asked him the thesis, laurea thesis, that he proposed me to work on the novembre in M31, a new work that was out of his first interest in galaxies, and I was instead interested in galaxies. So I accepted, and my first job was to blink 600 plates in Asiago, and this hard work led me to the discovery of 52 new novae in M31. You see, these are from my thesis work. And later on, with the collaboration of Massimo della Valle and Professor Rosino and Capaccioli, we arrived at the paper that Massimo della Valle have cited before, with the results that novae belong to the bulge population of M31. So I have to go fast, and when I started my PhD in Trieste, I asked Massimo to work on galaxies, and he proposed me to work on the Virgo cluster galaxies. And at the end of my PhD, I showed to Massimo this plot, and I remember that he reacted immediately, because this plot is for the first time the demonstration that early type galaxies are non-homologous stellar systems. And this was breaking a paradigm that elliptical and early type galaxies were considered homologous. So that means simple different in mass, but with the same properties, simply scale. So in this case, as you see, our surface photometry was realized by coupling Smith plate and CCD, the inner parts, and this allows us to verify that the brightest galaxies have this kind of surface profile, while the fainter one has this kind of, so the index N change from the lesser mass galaxy to the brightest galaxies. So this result was demonstrated for the first time that the non-homology of this stellar system. And this result is, so I'm very happy that two of my works are in the top list of Massimo publication. The result of non-homology is now well accepted in the community, and this is a recent work from Ferrarese, and demonstrates that non-homology extends over a very big interval of range in luminosity. So there is something that galaxies have for different index and different properties, but this result should be understood. So I tried I have to thank Massimo for this, because without him I didn't reach this result. So this is Massimo today, and now I can show you some two slides of Amarcord, because the next slide shows the true picture of Massimo in Texas, not the one that was shown by Pepe Longo. Okay, this is no, it's not Massimo, of course, but it represents the idea I had of Massimo when I was a student. A true hunter of astronomical discovery. So, but working with Massimo was not always easy, as Gianpaolo said us, because when you work with him, you have to forget the time, the watch, and what time is it. But this created at that time, that I was a young man, some problem in my life because I was in love with a beautiful girl that had not appreciated very much my phone call. I'm late, I'm sorry, I'm still working, and I cannot come. And she doesn't appreciate very much astronomy too. So the next slide shows what happens the day of the discovery of non-homology of elliptical galaxies. So we were in his office, very full of smoke, and I phoned to Mary. Mary, I have a great news. Elliptical galaxies are non-homologous systems. And she replied, Mauro, bad news. Your brain is not homologous. And so this was the end of a story of love. So I go now, joking, of course. When Massimo left to Padua to Naples, I tried to exploit as much as possible the legacy of this work on studying the fundamental plane. Why the fundamental plane is linked with the problem of non-homology, we will see in a moment. Briefly, the fundamental plane problem, we know that elliptical galaxies are a relaxed system for which the virial theory should be valid. And these are theoretical variables. You express the energy and the radius of the system with the mass. And when we translate the theoretical relation in observational one, we have to put this term which represents our ignorance of the structure of several things about the galaxies. So the virial theorem in observational terms can be written in this way, and these are the coefficients of the so-called virial plane. But what we observe observationally are different coefficients. It is a so-called problem of the tilt of the fundamental plane. When we couple these two equations, we can write this equation, which links if we add a third variable, which is the amount of dark matter, we can write this equation, which links the stellar mass derivation, this term which is unknown, with the velocity dispersion, the surface brightness, and constant. The first interpretation of the fundamental plane was, in fact, I go faster, that to have a tilt of the fundamental plane, you must have mass to light ratio varying with mass. And this is the first interpretation. But there is another possible interpretation, which involves this term kV, which could also vary. So that the interpretation is that galaxies are non-homologous systems, and so the tilt of the fundamental plane could be originated by the variable structure of galaxies as a function of mass. So I come back a little bit. So this term here give us the tilt, represent the tilt of the fundamental plane. And these are all variables that we measured, sigma, and surface brightness, and we have also measured masses of galaxies. So the only unknown now is this term. And we, using all this data, we looked at this variable and what this variable depends. And we see that the KV terms indeed depend strongly on the scarcity index. So this is a strong indication that the non-homology of early type galaxies is an important factor in determining the tilt of the fundamental plane. And this is confirmed not only by the WINGS data, but also from other surveys like Atlas 3D and Sloan. So we have now a reasonable data to say that the fundamental plane, that the structure of elliptical galaxies changes, and so these have a profound implication in the tilt of the fundamental plane. So I have to go very fast. It's saying that the stellar population effect is still there, but it is probably small, and probably the stellar population effect determines the differential tilt between the different bands. And then, so I conclude very fast that in order to have the tilt of the fundamental plane, there must be in place a strong relation between mass, structure, and stellar population. There should be some fine-tuning between the structure of the galaxies and the population which they host, depending on their mass. And so I finish and conclude that the fundamental plane is originated by fine-tuning in this structure of stellar population. And I have to repeat that without Massimo, this result was not possible. Thank you.
Okay, thank you, Mauro. We move to Magda.
Yeah. Yes, from there, right? Okay. So this is a constrained talk. We're obviously quite late. So I try to go to the essentials. The title is Planetary Nebulae in External in Galaxy Halos. I have expressed it as the quest for the green light sources. And here you see what the planetary nebula is in the Milky Way. And I'm asked to present it, and I'm very happy to do so, and mostly to honor the research that was done together with Massimo Capaccioli and also with the other collaborators, and some of whom are here with us today. And now let's see whether it works. Okay, yes. So you know about the spectrum of a planetary nebula, and so if you have a narrow band, you can see it's green light. You can also see in H alpha and not in broadband. And what it's really good for is when you are in very outer region of galaxies, where you have basically very little surface brightness. And now I say little means 1/100th of the skyscraper brightness. And you can still trace stars because these objects are related to the main population of stars. And you have about one planetary nebula every 10 million of stars. And so you trace the stars out in these very faint regions. What we know about planetary nebulae is that they follow a luminosity function that gives us distance. And the more distant the galaxies are, the fluxes become fainter. And still we can detect these single stars at very large distances, like 100 megaparsecs. And the reason why I got involved in this work is actually coming from a series of results that were obtained in the 80s and 90s. Planetary nebulae were started in the Milky Way, in the Magellanic Cloud, and also Ken Freeman was involved in this project. And so the idea was to try and detect them and use them to trace the velocity in the outer region, especially for elliptical galaxies. In spiral galaxies, we have gas, and so we know that there is a lot of dark matter there. So the idea was to use planetary nebulae. One problem that Mauro has already talked about is that the dynamical modeling is difficult. But still, if you have no velocity, you cannot infer mass. And also we had some technological problem because the nearest elliptical are the large distances, either the Virgo or the Forna cluster. And so the fluxes that we needed to detect was of the order of 10 to minus 17 ergs per second per centimeter squared. And you needed the best telescope and the most sensitive instrument. So how did it go? That is too fast. No. No, we missed, okay. Yeah, okay. So this work started when I joined Mont Stromlo for a postdoc, and it was actually an idea of Massimo Capaccioli to ask Ken Freeman whether we should ask for telescope time at TISO to do the observation of planetary nebulae in the Fornax cluster, which is a southern cluster and reachable with the New Technology Telescope. And so we did. And following the successful results of this observation, we started discussing about the possibility of building a slitless spectrograph. And there was 4 of us on a rainy night at the Silent Spring Observatory thinking we should ask Massimo whether he would like to join the idea of building a slitless spectrograph. And so this is how the planetary nebula spectrograph idea came about, and we also had support from Konrad Kolken, who was working in Groningen, and the planetary nebula spectrograph was commissioned on the William Herschel Telescope on July 20, 2001. Now, it's a very nice looking instrument, and it joins narrowband imaging with dispersed images. And it looks like a V. This is the real instrument, and you see it on the Cassegrain focus of the William Herschel Telescope. And the way it works is that you have 2 images, and the stars look like stripes, as you see here, and planetary nebulae are this monochromatic light. And now I know it's not going to work. Yes. So you can see that the little points are moving. And so in this way, you detect the planetary nebula and you measure the velocity during the same observing run, which saves time. And you can do this on a 4-meter telescope instead of an 8-meter, which also means that you have a lot of observing time. So here we go, the PNSK project. You see a lot of names here. We have the early type galaxy service now completed. We have about 40 galaxies. These are all the early type galaxies within 20 megaparsec that are visible for the northern hemisphere. And there's been a long series of papers that you see here, a lot of people that are involved with Naples, student of Massimo as well. And we're moving to the next project, which is the Bismuth project. I'm talking about survey data products are published. This is a long list of galaxies for which we have 2-dimensional velocity fields with the planetary nebula spectrograph or with the related technology. Here are the highlights. Halos are nice, but sometimes they behave differently from the inner part of the galaxy. The angular momentum can be quite different from the bright central region going outside. They can be fast rotator and then become slow rotator, or vice versa. And the other very important result from the planetary nebula spectrograph and Massimo legacy is this presence of the dichotomy in the outer region, where we have elliptical galaxies that show a quasi-Keplerian profile and indicate strong radial anisotropy of the stellar orbital distribution, while others have a rather flat velocity dispersion profile. And all these kind of galaxies live in dark matter halos. It doesn't mean that here we don't have dark matter for this Keplerian decaying profile. So moving on very quickly, We also detect substructures. This is for M31. This is a dissolving satellite in M49. So also in objects that look regular, when you look at the velocity, you are able to find something going on at large distances, and that tells you also about the assembly of the halos. Now, of course, the 8-meter telescope came about, and we embarked in a spectroscopic follow-up of planetary nebulae candidate. First of all, Rolf Kudrinski in 2000 claimed that there were no planetary nebulae in Virgo, and because they detected only Lyman alpha, redshift 3.14, and who cares about Lyman alpha galaxies? We are after planetary nebulae. And then in a series of work, we actually were able to obtain spectra from single planetary nebulae with the force toward the VLT. And the two results are consistent when we learned that intracluster light is associated with the densest region of the cluster and is not an homogeneous population of stars that fills the cluster up to the Virgo radio. And this is the sort of spectra that we are able to get now with flames, and you can tag the planetary and you can see the oxygen to that tablet. And this is a very interesting follow-up, and Alessia Longobardi results from the PhD thesis will be presented on Friday, so stay tuned. And the next step, reaching the nearest cluster is not enough, never for astronomers who are students with Massimo Capaccioli, always the more. And we were able to detect planetary nebulae in the Coma cluster and also in the other cluster. Quickly, this is a technique that expands on narrowband imaging and spectroscopy, and we call it multi-slit imaging spectroscopy. And the results were very instrumental in testing an idea which has been around for some time of the binary merging of BCGs in the core of the Coma cluster. And I know I have to be quick, but I can show you this is a very old photometry result from 200 Comedy that is based actually on the photometry also by Jorge Melnik, who is the one who first did the measurement of intercluster light in Virgo, in Coma. And this very elongated structure of the intracluster light in Coma is actually the result of this binary merging. And we were able to reconstruct it by measuring the velocity of the intracluster planetary nebulae in this red area. So moving on, this is what is going on now. We have completed the survey with the planetary nebula spectrograph. There is the dynamical modeling ongoing, and Nicola will also cover it. He's the last speaker today. We've also carried out this very extended survey of planetary nebula and M87. This is the Friday talk from Alessia Longobardi. We are moving on in the study of substructures in the halos. This is a wonderful result by Emily McNeil in 2010 on NGC 1399, where we have this very clear substructure which is seen face on the main distribution of light of the galaxy. And we are now doing an extension of the survey with the Subaru telescope for planetary nebulae around M39 and also extending the Dingo core. With the PNS is going strong. We have now started the Dismas project, and also we are reviving the VST because we understand that galaxies are so big, and we also think that there are lots of extended halo around this galaxy. Now we want to use the VST and buy a narrowband filter to carry out this survey. So Massimo, I think, should talk after in the next few days. And yes, so 2015 is the year of the stellar halos. There are two workshops that I want to bring to your attention. First of all is the ISO workshop in February 23rd, 27. The title is Baryons at Low Density, the Stellar Halos Around Galaxies. And deadline for abstract submission is December 12th. So if you are interested, please send your request for talk. And also there is the IU Symposium 317, titled The General Assembly of Galaxy Halos, Structure, Origin and Evolution. This will take place in August, the first week of the General Assembly in Honolulu, and You can see the address here to know more. And I would like to end by saying thank you all, Massimo, Ken, Ortwin, Nicola, and Alessio, for this exciting science, and I look forward to work with you in our future project.
Thank you, Magda. The next and the last contribution is by Nicola Napolitano on dark matter.
Yeah, I'm gonna kill you with a dark matter bullet. It will be very quick. Do you hear me?
Hello? So I couldn't really miss this talk, despite that we are very late. So I wanted to put this in a fair way, but I have to do hugging here instead of on behalf of Massimo. I mean, I can tell that he doesn't believe in dark matter, and I will show you why. He published a lot of papers. Here you have a list of the papers that he published, and 83 of these, about 200 papers are dark matter. And every time he could have the chance himself to mention dark matter, he didn't do it. So this is the distribution of the papers in dark matter from Massimo, and he worked on elliptical galaxy, right? So look at these two papers of dark matter. It was in 70s, so I said, maybe we worked in spiral galaxy, I didn't know. So I had to look at these two papers I didn't know about. Of course, it was a time, it was time that spiral galaxy was in the 70s. So I had to look at these two papers, and this is what it was about. So they're talking about the real presence of absorbing matter, and they call this patch, following the ocular, of course, patch of dark matter in bright diffuse lens. So there was some confusion about dark matter actually, and it was actually the time where, I mean, they were realized, it was even not on board at that time, that what was the dark matter. So the same in the 73. So then 90s came, and of course there was a time in the 80s where dark matter started to emerge also in the elliptical galaxy thanks to the works on X-rays, and you see here a paper from Fabricant, for instance, on M87, and you see the linear mass fluctuation going this way, say, telling, this is way to tell there is a lot of mass that you cannot associate with luminous mass. So dark matter is, at that time we learned how to call this kind of stuff. And so this was a work on NGC 3115, and you see that they demonstrated that the constant mass fluctuation couldn't fit the data, the dispersion data of this galaxy. They didn't even mention dark matter in their conclusion. Then the planetary nebulae came along, and Magda talked about this, the PNS, and things started to be a little bit more complicated. So you see here, it says mass fluctuation grow in gradients. So the way mass fluctuation grow with radius. And we have galaxies that grow very quick, and galaxies that are almost flat mass fluctuation. So we were convinced that most of these big growing things here for interactive galaxies, like this one you see here. So that was really exciting for Massimo. And in fact, this was one of the paper he wrote about it. And he was even more excited, I think, when we discovered with the planetary nebula. It was one of the first papers, science paper, where we discovered that this decreasing velocity dispersion curve were more compatible with no dark matter than a lot of dark matter. So, again, I think it was very happy about it. But, unfortunately, we went back to acquire more data, and we went back to the models, the sophisticated models, and this what actually had the bad news to give to Massimo about. And elliptical galaxy, also the one with a very strong decreasing velocity dispersion curve, are almost compatible with lambda CDM. Here you see the contour, the contour plot, and probably a little bit less concentrated than expected, but still consistent with lambda CDM. And of course, big guys are full of that matter, completely full of lambda CDM. So the magnet. So he said, come on, this is just Newtonian gravity. Why don't we try something different? Very different. So we went to this very exotic alternative theory of gravity, which FOR I'm forced to talk about, but I really like it. But so it's things that's right like that, but end up with some potential, which is actually a modification of normal Newtonian gravity. So why don't we try that? Yes, we tried, and of course everything worked perfectly nice. Perfectly nice, like one and things like that. One is that there are two parameters here, like in normal dark material, NFW for instance, and you can fit all these things almost the same way. And we found also this nice correlation between the parameters of this potential, which actually I can tell now after years that actually are not really what you end up with if you work better the theory, the fundamental of these FOR theories, and it seems that something goes rather perpendicular to this direction. So yes, we fit the velocity dispersion profile, but probably these are not really physical stuff. And so here we see another peak of production from Massimo. This is where we started then to think about kits and big service. So we get back to big sample of galaxy and look at the dark matter fraction in the central part of the galaxy. And here you see dark matter fraction in the very center, so velocity dispersion just in the center, Jeans equations, equilibrium in the center. And you see in the internal effective radius how the dark matter fraction grow with mass, with luminosity of mass. And lately we also discovered, actually there's something that Daniel mentioned already, and we actually came up with a paper probably a couple of weeks after yours. And we see that the dark matter fraction decrease, central dark matter diffraction decrease with redshift, which is something very interesting. But yet, dark matter seems to be there. So, unfortunately, Massimo legacy relies with the BST on the search of dark matter. I think that KIT and Atlas will tell us a lot about dark matter and dark energy, despite his resistance to the concept. So my personal view is that the relation with the dark matter was very difficult. If he really believed in dark matter, that dark matter was there, and I'm sure that he would have found it. The same way, with the same persistence he showed to have the VST working on Paranal. So you missed really a chance. And probably this could have also won you a Nobel Prize. So you have to just console yourself with the gold medal of the University of Moscow. And that's it, I'm sorry. There is one more thing. One more thing is that this is a paper where Professor Bertola and Professor Cavaccioli in 70 they found a new determination of mass dynamics 7, and they found that this galaxy has a mass of 2.7 10 to the 13 solar masses, and it has a mass fluctuation under 90 in 70. And this is exactly what we found today for the galaxies. So I think that you really missed the chance to pronounce for the first time dark matter. And so let us ideally give you the Nobel Prize, if you both maybe. So bad.
Thank you very much.